In this video, we're going to start our discussion of multiple regression, which is where we use more than one explanatory variable to predict a quantitative response. So we're going to go back to a familiar data set. This is the data set where we're using house size to predict price. And so far, we've just been looking at the relationship between size and price. That's simple regression when you have just one explanatory variable like size, and you're using that to predict a quantitative response. So our regression looked something like this. This is our line of best fit here. But it turns out that this model isn't really adequate. So we've talked about before that it seems like there might be some issues with the validity conditions, maybe some flared pattern where we think there might be non-constant variance. But another issue could be that we're not accounting for all of the relevant variables. So there's another variable in this data set called lake, which records whether the house is on the lakefront or not. So I'm going to color the points by lake. So I'll put that in the color box. And what I notice is that all of the lakefront houses are above the line and all of the not lakefront houses are below the line. So that means that this model is systematically underestimating the price for lakefront houses and overestimating the price for non-lakefront houses. So we definitely want to take location, whether it's on the lakefront or not, into account in our model. To account for more than one explanatory variable, we're going to do analyze fit model. So remember, fit y by x is for looking at the relationship between just two variables, a bivariate relationship. Analyze fit model allows you to include more than one explanatory variable. So I'm still going to be predicting the price, that's my response variable. But for the explanatory, I'm going to include both the square footage of the house and whether or not it's on the lake. And I'm going to run that. And there's a lot of output here. We're going to work through it slowly over the next couple videos. Let's start off by comparing the summary of fit. So now that we've accounted for location, our R squared is higher than it was before, 0.925. So 92.5% of the variability in prices is explained now, whereas it was less than half the variability in prices that was explained just based on size alone. We also see that the root mean square error is smaller. So that means that the typical size of a prediction error is smaller than it was before. So that's another way of saying that the predictions from our model are more accurate. We have less unexplained variability. Now let's talk about our slope and intercept terms. So before we do that, we have to think about how this location variable was defined. So we need to make it quantitative, right? Regression is when you have quantitative explanatory variables. And there's a couple different ways to turn a categorical variable like location into a quantitative variable. So the first one we're going to talk about is called effect coding. So when you do effect coding, you do 1 and -1. So like here, it says lakefront. So that's telling us that the positive one is lakefront. So we're doing a value of 1 if the house is on the lakefront, and a value of -1 if it's not on the lakefront. So we don't see those 1s and -1s in the column, although we could make our own column and define it that way. But this is what JUMP is doing behind the scenes. It's treating it as 1 and -1 based on whether the house is on the lakefront. So let's start by writing out our regression equation. So we're trying to predict the price of the house, that's y hat. The intercept is $95,430. I hope you don't mind, I'm going to round to whole numbers just to keep things a little bit simpler here. Plus 148, that's the slope for our x1, which is the size of the house, that's a quantitative variable. Plus 165,612 times x2, that's our lakefront variable. So what if we want to predict for houses that are on the lakefront? So this is when our x2 variable is equal to 1. So I'm just going to use my prediction equation and plug in, when I get to x2, I'm going to plug in a 1. So notice what happens there is now we have two constants. We have the one for the intercept, but then we also have this new value that came from lakefront. So this is basically adjusting the intercept. So I'm going to put those two terms together, those two constant terms together, and I get 261,042. And then I still have my slope related to the size of the house. Go ahead and pause the video and do the same thing for houses that are not on the lakefront. Come up with a prediction equation for those houses. So this works out basically the same way. We're going to be subtracting 165,000 this time. So we're still basically adjusting the intercept, but now we're adjusting it down because houses that are not on the lakefront tend to cost less than houses that are on the lakefront. And now we're back to just a regular linear equation. We've got an equation with a slope and an intercept. So this is defining two lines. The first one is the red line. This is the houses that are on the lakefront. We can see them in red on the graph. And then the second one here is the blue line. This represents the prediction equation for houses that are not on the lakefront. And both of these prediction equations have the same slope. That's actually an assumption that we're making in our model. So our model doesn't include any kind of interaction term. It's what we call an additive model. And so in that case, we're assuming that the lines are going to have the same slope for both of our groups. Now let's interpret the intercept and slope for our original model. So our intercept, we can see in the parameter estimates table, was 95,430. And if we think about how to interpret the intercept, it's usually the predicted value of y, the predicted response, when x equals 0. But now we have more than one explanatory variable. So here it's going to be the predicted response when all of our x's are equal to 0. So what would that mean in this context? It would be the predicted response. So this is the predicted price of a house. And we need to have all of our explanatory variables equal to 0. So the square footage would be with 0 square feet. So this is one of those cases where it doesn't really make sense to interpret the intercept, but we'll go ahead and do it now for practice. And then also the location doesn't really make sense either, right? Because what we have is 1 and -1 for lakefront and not lakefront. So this is sort of like in between. So you can sort of think about this as like the average house between lakefront and non-lakefront. So I'm going to put between in quotes because obviously that doesn't make a lot of sense either. Between lakefront and not lakefront. So on the graph, if you imagine a line for x2 equals 0, it would pretty much be like halfway between the two lines that we have. So this is the intercept in the middle between lakefront and not lakefront. Now let's interpret the slope corresponding to house size. So this is going to be very similar to what we did for simple regression. So in simple regression, we said it was the predicted change in y for a 1 unit increase in x. So we would say as the size of the house increases by 1 unit, which in this case would be 1 square foot, the price is predicted to increase. Remember, it's always important to say predicted to or tends to or on average, something like that, to make it clear that there is variability around the line. Price is predicted to increase by this amount, so $148. So far it looks just like simple linear regression, but in multiple regression, we're going to add this tag at the end holding the other variables constant. So in this case, it would be holding location constant, which basically means that we can't compare a house on the lakefront to a house that's not on the lakefront in terms of size because we have different regression equations for each one. So this is telling us the slope of one of those two lines. It's not the slope if you just ignore location and look at it overall. We actually got a different value for the slope when we did simple linear regression. Sometimes you'll hear it phrased differently, like controlling for location or adjusting for location. Those would be fine too, but something to acknowledge that we're looking at the two locations separately, that we have different prediction equations for each one. Now let's look at the slope corresponding to location. So this is the one that's really new because this is a categorical predictor in a regression equation. So the interpretation is going to be a little bit different, but it kind of makes sense if we go back to the definition of slope as the predicted change in y for a 1 unit change in x. So what does a 1 unit change in x mean in terms of this effect coding? So 1 unit change in x would be like going from 0 to 1. Remember we said 0 is like this dotted line in the middle. This is like the average regression line, the one in between lakefront and not lakefront. And we're talking about the change in price as we go from that line up to lakefront. So basically, as we go from the average up to lakefront, we're adding $165,612. That's our predicted increase in price as we make that change. So the difference between the predicted value for lakefront compared to the average predicted price, to go back to language that we used when we were doing ANOVA, that's like an effect. So this is the predicted effect of being on the lakefront. And it's still multiple regression, so it's still important that we add that tag holding the other variables constant. In this case, holding size constant. So that means that we can't just compare any lakefront house to any not lakefront house because we want to take size into account. But if we look at one particular value of x, like the line I drew, it looks like it's maybe at, I don't know, 2,800 square feet. We can say for a house of any given size, this is the effect of location. This is the effect of going from the average to a lakefront house. So conceptually, I know it's a little bit difficult to think about this middle line since that doesn't actually describe any real houses. We have to kind of like conceptualize it as the average or the in-between. And because that can be difficult, we're actually not going to spend a whole lot of time on effect coding in this class. We're going to transition over to something that may be a little bit easier. The reason that I wanted to bring it up, well, there's two reasons. One is that it is the default in JUMP. It's good to be familiar with that kind of output because that's what you would get if you just did analyze fit model and you didn't make any changes to the estimate table. But the other reason that I wanted to bring it up is because it's connected to what we did with ANOVA. So let's rewrite this regression equation in terms of the effects like we would have done for ANOVA. So we've got our predicted price, and we still have our intercept that was 95,430 plus the slope 148 times size. That's what we're plugging in for x1. But now I'm going to write the location variable like we would have done in a past unit. So I'm just going to do this as the two effects. So we're going to add 165,612 if it's on the lakefront, and we're going to subtract that amount, subtract 165,612 if not on the lakefront. So that's essentially what we did before, right? We just adjusted based on whether it was lakefront or not by plugging in 1 or -1. But writing it this way, I think it looks a little bit more familiar. So this also means that everything that we did with ANOVAs a few weeks ago, we could also do with regression just by coding it as a quantitative variable. And we'll make some of those connections along the way.